We end this lecture with looking at a two-unit parallel system, but with dependence between the two units, and thereby bring out some interesting observations. So the two units are in parallel, so the system failure event is still F1 intersection F2, but the reason that the two units are dependent, F1 and F2 are dependent, is because of the presence of a common cause. So F1 is FCC, which is common cause, union FE1, and F2 is FCC union FE2. So what are E1 and E2? E1 and E2 are events that constitute part of the unit 1 and E2 for unit 2. The common cause E1 and E2 are all mutually independent, but because CC shows up in both 1 and 2, it causes dependence between the failure events F1 and F2. Let me show you the reliability block diagram. We haven't introduced it, but it's quite intuitive. It clearly shows how the events are connected. E1 and E2 are in parallel, but common cause is in series with them. And so E1 and CC together constitute F1, and E2 and CC together constitute F2, and thereby F1 and F2 are dependent. So we want to find out the failure events of F1, its probability of F2, and the system failure probability, as well as the conditional failure probabilities, in terms of the relative values of the common cause failure probability and the E1, E2 failure probabilities. We take the simplest assumption that the problem is symmetric in F1 and F2. So E1 and E2 are identical. So P of FE1 and P of FE2, each is equal to P, and the common cause failure probability is P prime. And let us now derive the P of F1 and P of F6 and so on in terms of this P and P prime. So P of F1 by definition is P of FCC union P of F1, and if we expand it, we come up with the usual P of A plus P of B minus P of AB. And by putting in the values, because now they're independent, FCC and FE1 are independent, so it's simply the P of F1 is P plus P prime minus P prime. Because of symmetry, P of F2 would have an identical value. So we have derived the probability of individual element failures in terms of the common cause failure probability. The next would be to derive the system failure probability, so which by definition is F1, F2. So if we expand F1 in terms of the common cause and F2 in terms of the common cause, then we can work through the steps. P of F6 is P of F common cause union union FE1, FE2, and then by expanding that and bringing in the fact that they are all independent now, we can express the system failure probability as in terms of P prime and P of the E1 and E2. So we have derived P of F6. Now, for the sake of completeness, let's also find out the measure of dependence, because F1 and F2 are not dependent. They are related to the common cause. So let's find out P of F2 given F1. It also turns out that because of the nature of the system, P of F2 given F1 is also P of F sys given F1. By definition, P of F2 given F1 is P F1 F2 over P of F1, and we have already derived each of those. So that would be P prime plus P squared minus P prime P squared over P prime plus P minus P prime P. By symmetry, P of F2 given F1 is also the same as P of F1 given F2. Now let us see how the common cause failure probability P prime affects the entire picture. So let's go to the next slide, and this is what we have. We have found out P of F1 and F2 individually. We have found out the system failure probability. We have also found out the conditional failure probabilities. Now let us put 4 possible values of P prime in relation to P. So the common cause failure probability in the ideal case, in the case that we assume that F1 and F2 are independent, so P prime is 0, so there is no common cause. Then there's very small P prime, which is 1,000th of P, so only 0.001 P is there as the common cause failure probability. The third possibility is that P prime and P are equal, and then P prime is huge. So the common cause failure probability leads. It's the dominant failure probability. So what happens to P of F1 or P of F2? So when there is no common cause, then we go back to the classical case. So P of F1 is P. When there is a slight common cause probability, so it's 10 to the power minus 3 times P, so 1,000th of the independent event probabilities, then P of F1 or F2 is just slightly larger, so it's 1.001 P. When the two are equal, we have twice P, so the failure probability of 1 and 2, they become double. And then when the common cause dominates, then it's obviously that, so 1001 times P. But what happens to the system failure probability and what happens to the conditional failure probability? Let's take a look at that, and that will be very instructive. So when P prime is 0, then the system failure probability, as we know, is P squared. But when P prime is as little as 0.001 P, which is the second row, then we see a huge increase in the system failure probability. It is P squared plus an addition of 0.001 P. So if P is small, if say P is the order of 10 to the minus 4 or 5 or 6, then that second term, that 0.001 P, starts to dominate. So even a very small common cause is going to have an overwhelming increase in the system failure probability, and that's the same thing which happens in the conditional failure probability. When they were independent, F2 given F1 was still P, but when there is a slight common cause, then it goes up by 0.001, and if P is of the order of minus 6, then obviously you can see that the common cause starts to dominate. When P and P prime are equal, then the system loses all benefit of being in parallel, so the probability of system failure is now equal to P instead of P squared. The conditional failure probability of F2 given F1 is half, as much as half. And when in the last row P prime starts to dominate, then obviously P of F2 given F1 is practically 1. So if one fails, the other is almost certain to fail, and the system failure probability is enormous. So it's 1,000 times P. Obviously, there are approximations in these expressions. I've taken P to be small enough. But the idea is there is a potentially huge contribution to common cause failure when two units are in parallel, but they are not independent.